Welcome back to the lab. Today we're going to design and build our inverter test platform for Project Darwin. This project has been a great ride so far, and I cannot wait to see what it develops into with a little more love. We've talked about a few key parts of the project, like the system architecture and a couple different implementations of inverter output stages that we were considering. We've also been introducing some of the concepts that are more fundamental to the design, such as microcontroller selection, where to buy components when you want to put them on a board, and stability and control loops. Now, let's capture this design in KiCad and assemble our design. When designing this power stage, there really wasn't a whole lot to it. There are two I/O headers available. One is for the 5-volt tolerant microcontrollers, and the other is for 3.3-volt microcontrollers. The analog signals come through both headers without additional scaling, so the maximum measurable output voltage is higher for the 5-volt header than the 3.3-volt microcontroller. However, both of these voltage ranges are sufficient for our application since they both exceed 50 volts. There are a few test points thrown around the board to hook up scope probes to voltage current monitoring, ground, and many female banana plugs, one for each power input or output in the system. In this case, that's 12, 5, the high power output, and ground. There is a large capacitor bank of 33 millifarad 50 volt caps, which are used as the input capacitance for the system. Since we may want to take the inverter to higher voltages than that, I added banana plugs to be able to add or remove that capacitance from the circuit as required. While this adds some extra impedance between the bulk caps and the power stage, I think this is a minor trade-off for getting the added flexibility of being able to take our DC bus voltage up to 300 volts, if we ever want to. With these components considered and a logic level shifting circuit in place for the 3.3 volt header, all that's left for us to do is implement the isolated gate drive ICs with bootstrap caps and gate drive modification passive component placeholders on the board. These allow us to change things like the slew rate of the gate drive signals to tweak the FET timing a little bit. After we've placed some FETs and a Hall effect current sense chip, we're pretty much done. One half of the output stage was designed, so I just duplicated it to create the other half H, and now we're ready to head into layout. This board really gave me an appreciation for how large the output inductors, bulk caps, and heat sinks are with respect to every other component in the design. This board needs to be pretty large, approximately 7 by 6 inches, or 180 by 143 millimeters. The critical routing here is keeping those gate signals for the FETs as short as possible and as close in length as possible for one another. Everything else should be routed as well as practical, but there isn't really a whole lot going on and there aren't a lot of critical nets. That said, I have an internal power and ground plane to provide a wide current path for the power nets and routed the additional signals on the outer layers. This allows for sufficient trace width to handle the 10 amp output current of the system with minimal temporize in the copper traces. Now all we need to do is wait. I ordered our fabs and parts, immediately getting to work with assembly after they arrived. It took somewhere on the order of 10 hours to assemble, all told. While we finish up the assembly, let's talk about what this board is supposed to do and what it's not supposed to do. This board, the proof of concept inverter, is not meant to be the final design in any regard. It's meant to get us close enough to the final design so that we can find issues in the system and resolve them. Why? I have big hopes for this project. I have hopes that I'll be able to coordinate a small quantity prototype run for the surface mount parts in China, build it to a form factor compatible with standard ATX motherboards and cases, and really a lot of time, effort, and thought are going to be required when building the final board to get the battery balancing, the DC to DC and AC conversion all talking nicely together. And if there's a fundamental flaw in the design for the output stage, I'd rather find out now before I spend all that time getting the form factor right, coordinating the prototype manufacturing run, all that extra stuff. This board will let us power up some electronics, get an output voltage of 120 volts, tune our control loops, and make sure that we have a proper voltage regulator. And this is before we need to worry about the charging batteries, all the other conversion, overcurrent protection, switching between power sources. I think you get the point. It was an incredible feeling to watch this board come together on the bench. I could just smell the progress in the air. Or is that the smell of burning ICs? It's always been hard for me to tell the difference. The inverter board will need some software, which we'll cover in our next Project Darwin video. We'll be implementing a DC voltage regulator first, tuning our control loop around it, and then switching over to AC. Well, that's all for this installment of EEforEveryone. Let's close this out. I think that this board turned out great. If you can't wait to see it powered on, let me know by hitting the like button on this video, subscribing to the channel, or leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye!